Alright, today I'm going to start to talk about differentials. In all honesty, I think what would be the easiest thing for me to do is go ahead and start a problem, and then I'll describe to you what differentials are a little bit further. So in this first problem, what I'm going to do is I'm going to find the equation of the tangent line to the graph of f at the indicated point. And then I'm going to use this linear approximation to complete the table, which is what we're doing with differentials. We're using a linear line or a linear equation to approximate what the actual value is on the function itself. So what I'm going to do is I'm going to actually find this derivative because I need it. This is actually 6x to the negative second. So my first derivative is negative 12, x to the negative third. So I'll rewrite that as negative 12 over x cubed. This is going to let me be able to find that tangent line to the curve. So my tangent line of the curve will be y equals, or let me change that a bit. Let's put it in point slope form. Y minus 3/2 equals, I'll go back and fill my slope in a minute, x minus 2. The slope is figured out by plugging in my 2 right here. The slope at 2 will be negative 12/8. Negative 12/8 reduces to be negative 3/2. I don't really like the way this is written. I'm going to have it as a y equals equation, so I'm going to go ahead and say y minus 3/2 equals negative 3/2 x plus, that would be 3. And then I'm going to add 3/2 to both sides. When I add 3/2 to both sides, I end up with negative 3/2 x plus 4 1/2, which would be 9/2. Now, at this point in time, I would use a calculator just to save some time, because what we're going to be doing is we're going to be plugging in 1.9 to the function value, and we're going to plug in 1.9 into the tangent line. And what we're going to do is we're going to show how these are very close to each other. So I will quick bring up a calculator. I'll just bring up a small calculator. I wouldn't recommend using the small calculator. But what we're going to do is I'm going to go ahead and put in 1.9 in for my function value. So I would say 6 divided by 1.9 squared, or 1.9 times 1.9, is equal to 1.662. So I get 1.6620 in this case. Now I'm going to use the tangent line to the curve. The tangent line to the curve is right here. And I'm going to go ahead and plug in 1.9 in for there. So I have a negative 1.5 negative 1.5 times 1.9 equals, and then I'm going to add 4.5 to it for a total of 1.65. Notice how the tangent line to the curve was very, very close to the actual height of the function, and that's what we're really talking about in differentials, and I will get into that in the next video. Let's go ahead and continue this and show how 1.99 also is going to be very close. So when I plug in 1.99 in for here, I have 6 divided by 1.99 times 1.99. That gives me the answer of 1.5151. And then if I take that same value, 1.99, and plug it in for the tangent line, I'll let you guys do that on your own because I'm running out of video time. But you will get 1.515. Again, very, very close. We'll finish this up on the next video. Alright, so I was talking about how we're going to use tangent lines to approximate actual function values. And I was at this point where I was getting ready to plug in 2. When I plug into 2 into this right here, I get 6/4, which is 3/2, which is 1.5. And when I plug into here, I get negative 12/8, which is, or not negative 12/8. I need to plug that into the tangent line to the curve, not into the function. So I'm going to plug 2 in for here. I get negative 3/2 times 2 plus 9/2. Those cancel, so I have negative 3 plus 4 and 1/2, which is 1.5 as well, which is what I should get because these two, the function and the tangent line, share that common point. So I should be getting the same values there. As I look to the right of this, something very, very close to 2. Remember, what we're trying to do is use a tangent line to approximate the actual height of the function. And so when I plug in 2.01 into, first of all, this function up here, I get 6 divided by 2.01 times 2.01. That equals 1.4851. And then I will take that same 2.01 and plug it in for the tangent line to the curve. So in this problem, then I would get 1.5, a negative 1.5 times 2.01 equals this plus 4.5, which gives me 1.485. Notice how these are very, very close. And that's what you can see in the graph, that there's very little difference between the tangent line and the function value. You'll do that one more time for 2.1, and of course there would be a greater gap between these two because we're getting further away. So the further away we get from that point, the greater our difference between the actual function value and that tangent line is. That's what we're doing when we're using differentials. A differential is a dy over dx. We've seen dy over dx's in our derivatives. dy over dx equals f prime of x. I could solve for dy over dx, or for dy, by multiplying by dx on both sides. I do want to go ahead and show you that. So we're going to denote dy is equal to f prime of x dx. What you saw in that last example was how I was using tangent lines to approximate the actual function height. The actual change in y, okay, the distance between these 2 points, the y distance between them, we'll call change in y, is very, very close to what that height value is of that tangent line to the curve. Remember, it was really, really close the closer and closer we got to that point of 2, and it was getting further and further apart the further and further away we get from that point. What I want you guys to take note of is that we're going to decide or make note that the change in y is approximately equal to dy. It's not equal to dy. We saw how these were not equal to each other, but they're close to each other. So the last comment I want to make from this is that dy, since it's approximately the change in y, it would be approximately equal to, so the change in y is approximately equal to f prime of x dx. I'll continue with some other examples in the next video. Looking at this picture, I want to go ahead and do one more thing. I want to go ahead and mark this point right here, and I want to call this x comma f of x. And then this point up here would be denoted as x plus change in x, okay, because we're moving across some distance of x here. And then the new height would be x plus change in x. x, or f of x plus change in x. And we've done this before when we were driving the derivative. Well, what I'm going to take note of is that the change in y, and this is what I want to write down here, the change in y is equal to the y minus the y coordinate. So our y coordinates would be f of x plus change of x minus f of x. We're going to need this knowledge as we continue on. So we're going to be using this and the dy equals f prime of x dx. This next example asks me to compare the change in y and dy. So I'm going to go back to the slide. I want to make sure I copy down both of those equations I have in boxes. One said change in y equals f of x plus change in x minus f of x. And then the other one said dy is equal to f prime of x dx. What I'm supposed to do is I'm supposed to compare change in y and dy. We should see that they are pretty close to each other. So I'll go ahead and start by finding change in y first. What they give me is they give me my x is 0. They give me my change in x is negative 0.1. So I'm going to plug in the 0 for the x and the negative 0.1 for the change in x. Then what I'm going to do is, this really says find f of negative 0.1 and subtract it from f of 0. I'm going to plug in negative 0.1 into this equation. So it'll be 1 minus 2 negative 0.1 squared minus what f of 0 is, which would be 1 minus 2 times 0 squared. So all I did was plug in negative 0.1 in for my x and then 0 in for there. What that gives me is that my change in y is equal to, when I punch that all into a calculator, reduce it, negative 0.02. On this other part here, I know that dy is equal to f prime of 0 dx. Now my dy is equal to, let me go ahead and separate those two. I need to know what f prime of 0 is. Well, in order to do that, I need to know what f prime is. So y prime is equal to negative 4x. So I'm going to take and I'm going to plug in 0 in for here, and I will end up getting negative 4 times 0, and then times my change in x, which would be negative 0.1. When I multiply that together, I get dy is equal to 0. Notice how these are very close values to each other. I have one more video that we will cover. Okay, my last example for day 1 will be to find the differential dy given the function. Really, all we need to do to find a differential is to take the derivative. So what I'm going to do first is just go ahead and rewrite this. 9 minus x squared to the 1/2. I'm going to take the derivative, dy over dx is equal to, bring that out front, 1/2. Rewrite this and lower it by 1. Take the derivative of what's inside, which is negative 2x. So I end up getting dy over dx is equal to 1/2 times 2 makes a 1, so I get a negative x over, this is on the bottom of the fraction, square root of 9 minus x squared. Now I need to find dy over dy, so I'm going to multiply both sides by dx. This is as far as I need to take this. This is the differential and the answer to this problem.